In this video, we're going to review finite limit techniques. Limits are a tool that help us study the behavior of a function near a point. In the following, we're going to learn a series of finite limit techniques, and these are going to reveal to us, they're going to help us understand why the function behaves as the limit tells us near a certain point. There is another technique that we're going to study later called L'Hopital's rule, and this is a very powerful tool, a very useful theorem. However, its disadvantage is that it really simply gives us the answer to a limit. It doesn't explain why the function behaves as it does near the point. So it is very useful for us to learn these finite techniques that I'm going to present next, because they're really going to shed some light into the behavior of the function, whereas L'Hopital simply gives me a number. So we start with the first technique, namely that of evaluating. So this technique trumps all other techniques when it comes to limits. You're always going to try to first evaluate your function at the point where you're computing the limit. So for example, let's say we have the limit as x approaches 0 of e to the 2x minus cosine of x. So we have the function e to the 2x minus cosine of x, and we want to know how the function behaves near the value of x equals to 0. And you're always going to start by plugging 0 into your function. So what we obtain here is e to the power of 2 multiplied with 0 minus cosine of 0. So we simply took the 0 and evaluated into the function, and we obtain e to the 0th, which is 1, minus cosine of 0, which is 1, so 0. So this tells us that the graph of the function as you approach 0 from the left and from the right is going to attain the height of 0. Again, we were able to compute this limit simply by evaluating 0 into the function. Being able to compute a limit simply by evaluating is not always going to happen. Namely, in most of the cases, we're going to encounter some hurdles. For example, in the case of a rational function, we might encounter the hurdle of the indeterminate form 0 over 0. So let's look at an example. Let's say I have the limit as x approaches 3 of x squared minus x minus 6 over x squared minus 4x plus 3. So when we try to evaluate 3 in the expression, we get in the numerator 9 minus 3 minus 6, which is 0, and in the denominator 9 minus 12 plus 3 again gives me 0. So we encounter this so-called indeterminate form 0 over 0, which represents a hurdle in me trying to compute the limit as I did before, simply by evaluating. So what is an indeterminate form? So again, this 0 over 0 happens to be one such indeterminate form. It is a hurdle that we sometimes encounter when we compute limits, and what this means is that the answer to your limit could turn out to be anything. It could be 5, 100, minus a million, it could be any number. It could also be infinity or negative infinity, or the limit might not exist in general. So what we need to do is develop a series of techniques in order to overcome this hurdle and still be able to compute these limits. So what we're going to do in the case of a rational function and 0 over 0, we're going to try to identify the source of this 0 over 0. Namely, since when I evaluated the numerator at 3 and I got 0, that means there must be a factor of x minus 3 in the numerator. So let's try to actually factor the numerator. Give me two numbers, then multiply to negative 6 and add to negative 1. That's going to be x minus 3 and x plus 2 And as you notice, as I predicted, I have a parenthesis of x minus 3, which is the source of the 0 in the numerator. And let's do the same thing for the denominator. Give me two numbers, then multiply to 3 and add to negative 4. That's going to be x minus 3 and x minus 1. So I noticed that the source of the 0 over 0 was given to me by having a parenthesis of x minus 3 both in the numerator and in the denominator. So in order to overcome this hurdle when I'm dealing with a rational function is we're going to factor and we're going to cancel the source of the 0 over 0, namely this parenthesis of x minus 3. So what I'm left with in this case is the limit as x approaches 3 of x plus 2 over x minus 1. And now if I evaluate at 3, I no longer encounter a hurdle. I simply get 5 over 2, and this is the answer to my limit. So again, the technique when dealing with a rational function and encountering the 0 over 0 is going to be to eliminate the source of the 0 over 0 form. Namely, we're going to have to factor both the numerator and the denominator, and we're going to cancel the source of the 0 over 0, namely if I have that my rational function becomes 0 over 0 at 3, then I'm guaranteed to have one such parenthesis, x minus 3, both in the numerator and the denominator, that when we cancel, we're going to eliminate the problem and be able to just compute the limit afterwards by evaluating.